All right, so let's go ahead and try this again. This is take two of part two of section 5.2. It's a lot of twos, but we're just going to get into the energy diagrams to go along with the electron configuration. So let's go ahead and pick off where we left off. So what we need to know next is that the electron configuration can also be used to organize our electrons in terms of energy. We're talking about relative energy. Now, it's important to understand because a lot of these electrons that we have are not all the same. Some of them carry more energy than others, and so some of those will be more reactive than others. And this property will be very important for determining bonding and seeing how our atoms interact with each other. So, one more time, these energy diagrams help us organize all our electrons in an atom in order of increasing energy. And it's important to know what electrons have the most energy because electrons that have a high energy are also very reactive. So, when we're predicting the outcomes of a lot of our chemical reactions, we need to know which electrons are the ones that are involved. All right, so let's look at this template over here. So it's just a blank template that we can use for organizing all of our electrons. Notice that I have the nucleus down here at the bottom, and I have all these spaces to put in the electrons. So this represents an atom directly, and again, the farther that I get away from the nucleus, notice that my energy here is increasing as I go out. So the farther I get from the nucleus, the more energy that these electrons will have. The harder it is for the nucleus to keep the electrons in check. All right, so notice that I also have all these labels on this diagram here, where I have the 1s, 2s, 2p, 3s, 3p, and so that's kind of familiar. It's the same type of order that we see in the electron configuration when we had that 1s2, 2s2, 2p6. So again, here's just written out that I have these different orbitals. Here's the names of them, and then how many electrons are in each orbital is written in the superscript. In this energy diagram, I'm actually drawing out the orbitals, and then I get to draw in the electrons and exactly where they're placed. For each of these lines, you'll notice that some have just one line, some have three lines, some have a set of five lines, something like that. Each single line represents a suborbital, and in each suborbital, you can have two electrons. And the way that we draw our electrons is that we use arrows to show what their spin state is. So here we have two options because electrons, they can either be spinning in a clockwise direction or in a counterclockwise direction. But to simplify it for us a little bit, we just use either an up arrow or a down arrow to show which way they are spinning. Let's see how we actually use our energy diagrams for this. So now when we make these diagrams, we need to follow three rules in order to have them be correct and show us the right information. The first one is called the Aufbau principle. And Aufbau is a German word that means to build up. So very simply, it just means that we need to start from the bottom and move our way up. We're starting in the inner orbitals that are closest to the nucleus, and we're moving our way out. Next is the Hund's rule, which means that when we have multiple suborbitals, we need to fill in one electron at a time before we can start to double up in a single space. I'll show you more on what that means when we actually build one of these. And then finally, we have the Pauli exclusion principle. This is at its core saying that no two electrons can be identical. If they are in the same suborbital, they can't have the same spin state. So what that means is that we can't draw two arrows in the same direction in the same line on our energy diagram. All right, so let's actually look at an example and see how this is done. So let's say that we're looking at neon, and it's number 10 on the periodic table, and if you find its electron configuration, it should be 1s2, 2s2, 2p6. So let's actually see how we can take this electron configuration and put it into our energy diagram. All right, so first, if you go through and you count up all the electrons, those are the superscripts of our electron configuration, we'll get 2, 2, and 6, and this will give us 10 electrons total, which means that we need to put in 10 electrons into this energy diagram. Now let's start with the Aufbau principle. We start from the bottom, so first up we have that 1s orbital. 1s, and in this I'm showing that there will be two electrons. So in this I'm going to fill in the electrons using arrows. First one up arrow and then a down arrow. So that takes off our 1s2. I'm showing the same information here with the arrows. Now let's move on to the one that comes next, 2s. So moving one up, 2s, and again, I'm saying that there will be two electrons in that. So we'll start with one up arrow and one down arrow. Now, what comes next is the 2p orbital, and you can see that this one is different from the s orbitals that we've done, where we have three spaces to put in. This is where we have to start using Hund's rule, where we can only put in one electron at a time for each line. So again, we have 6 electrons to put in. We have three spaces, two in each. So first we'll start with one up arrow, two and three up arrows, one in each of the lines. Now, once we have done that, we've maxed out all our single electrons. We need to start to double up and start putting in down arrows. So let's go ahead and do that. So this is 4, 5, and 6 electrons. So if you go through and you count all these individually, this will all add up to 10 electrons, all in the 1s, 2s, and 2p orbitals. All right, so now let's look at this final example. Let's say that if you were given an element with a certain electron configuration like this oxygen with the 1s2, 2s2, 2p4, and you were given the option of two different electron diagrams, which one would you choose? Which one would be correct? So if you go through this example of oxygen and you take the superscripts, so 2, 2, and 4, and you add them all together, you'll see that oxygen will have 8 electrons total that you need to put into this energy diagram. And if you go through these two examples, you can see that they both have 8 electrons. So now how do you choose which one is correct? All right, so this comes down to the Hund's rule, saying that you have to fill in every single line with a single electron before you can start to double up. So when you remember that, and you see this example over here on the right, you can see that you have um, two electrons in the first suborbital, two electrons in the second, but in the third, it is completely empty. And you can't do that. You can't start to double up your electrons while you have empty spaces. So for that reason, this diagram on the right is breaking Hund's rule. So this would be the one that's wrong. The one that is correct is the one on the left, where you have 3 up arrows and then 1 down arrow in the 2p orbital. All right, so just keep that in mind. If you ever see problems like this, just make sure that you keep in mind the 3 rules for energy diagram. So that's the Aufbau principle, start from the bottom, move to the top. Hund's rule is that you have to put in one electron in the on all the lines before you can start to double up with down arrows. And then the Pauli exclusion principle is just that you can't have two up arrows or two down arrows in the same space. All right, so just keep those in mind, and I don't think these electron diagrams should give you too much of a problem.